In this lecture, I am going to continue to talk about phasors, and we're really just going to do a bunch of examples of working with complex numbers. One, so that way I know that you have some experience with it, and two, so that way you can make sure that your calculator is spitting out the same answers that I'm getting. So we're going to start right away with example number 1. In this example, I want to evaluate the following complex numbers. The first one, A, is going to be 40 angle 50 degrees plus 20 angle negative 30 degrees, all to the power 1/2. That means the square root of it. And B, I'm going to take 10 angle negative 30 degrees plus 3 minus j4 over 2 plus j4 multiplied by 3 minus j5 complex conjugate. Or essentially, I'm trying to throw as many things at you at one time as I can. Now, I want to highlight before you start working these problems out that you need to make sure that your calculator is in degrees mode, not in radians, or you will have some issues. All right, so let's start with part A. So in part A, I have two things that I want to add together, but they're both in polar form. But we know that it's much easier to add in rectangular form than it is to add in polar form. So we need to convert from polar to rectangular form. So 40 angle 50 degrees is 40 times the cosine in degrees of 50 degrees plus j times 40 times the sine of 50 degrees. If you type this into your calculator, you should get 25 My ability to write and talk at the same time is woefully bad. 25.71 plus j 30.64. Similarly, for 20 angle negative 30 degrees, that's going to be found by taking 20 times the cosine of negative 30 degrees plus j 20 times the sine of negative 30 degrees. And that gives me 17.32 minus j10. And so I can add these things together. So let's do that. 25.71 plus 17.32 plus j times 30.64 minus 10. This is equal to 43.03 plus j 20.64. Yikes. Now, the last piece I need of this is I need to be able to take the square root of it, or take it to the 1/2 power. In order to do that, the thing that I'm going to want to implement is that I might want to get this back into polar form. So let's convert this to polar. In polar form, I've got the square root of 43.03 squared plus j 20.64 squared. That's my magnitude with an angle, and because the real part is positive, I've got just the angle of the inverse tangent of the imaginary part over the real part, which is 20.64 divided by 43.03. When I calculate this out, I've got 47.72 angle 25.63 degrees. And then if I take the square root of this, that's the same as raising it to the 1/2 power. And I know that I could also write this as the exponential e to the j 25.63. So if I take it to the power 1/2, that's the same as taking this 25.63 and dividing it by 2. So that's equal to 47, So I want to take this whole thing to the 1/2 power. That's the same as taking the square root of 47.72 and then taking e to the j 25.63 divided by 2. Which leaves me with 6.91 angle 12.81 degrees. And I'm done with part A of the problem. All right, let's move on to part B. In part B, I have this really complicated thing, so I'm going to go ahead and do this. Let's make a copy of it and put it down here, so that way I've got, let's see, paste. That way I've got it, so that way you can see it. This is apparently pretty involved. So the first thing I want to do is, I know in the top I can add. I don't really want to add a polar form with a rectangular form, so I'll convert 10 angle negative 30 degrees into rectangular form. So that's 10 times the cosine of negative 30 degrees plus j times 10 times the sine of negative 30 degrees. Altogether, that's equal to 8.66 minus j5. And then I'm going to add that to 8.66 minus j5. I'm going to add with 3 minus j4. That's equal to 11.66 minus j9. Then I can go to the bottom part. In the bottom part, I have two options. The first is that I could convert to polar and then multiply and then convert maybe back to rectangular. I'm not sure if that's a good idea. Or I could just use polynomial multiplication. And I know that the complex conjugate of 3 minus j5 is just equal to 3 plus j5. So why don't I just multiply these out? I've done polynomial multiplication before. So that's 2 plus j4 multiplied by 3 plus j5, which is equal to 2 times 3, that's 6, plus j4 times 3, plus 2 times j5, plus j4 times j5. So altogether, that yields, let's do that, it's equal to 6 plus j12 plus j10 plus 20 times j squared, which is equal to minus 20, right? So this equals to 6 minus 20, so minus 14, plus j22. Alright, so now I know the following is true. I know that what I'm looking for is 11.66 minus j9 divided by minus 14 plus j22. Now I have a good case to move this into polar form. So this is equal to the square root of 11.66 squared plus 9 squared with an angle inverse tangent of negative 9 over 11.66. And then I can divide that by the square root of 14 squared plus 22 squared. And then this tangent is going to, this angle is going to be a little goofy because I've got the inverse tangent of a value where the real part is negative. So this is going to be 22 over negative 14, but because I have a real part that's negative, I have to add or subtract 180 degrees from that, which is going to give me the value of the angle. So let's go ahead and get those together. So this is equal to 14.73 over 26.08. The top part has an angle of negative 37.66 degrees. The bottom part has an angle of 122.47 degrees. And I just want to highlight here that this bottom part, if I look at it, I'll remind you I've got quadrants 1, 2, 3, and 4. The bottom part, 122 degrees, is somewhere in quadrant 2, which means that it really looked like it's here. If I just take the inverse tangent of 22 over negative 14, that has no way of knowing if that argument is negative from the numerator or the denominator. And so since it's negative, it pops up in quadrant 4, so I have to add this 180 degrees to it to get this answer. Now I can go ahead and do the division. It's equal to 0.565 angle, and then I'm going to take this top angle and I'm going to subtract from it 122.47, which is equal to 0.565 angle negative 160.13 degrees. Whew. That's a big problem, but that is the most difficult example we're going to do today. The rest of the examples are a little more applied, specifically to phasors. At this point in class, I would stop and say, are there any questions? That is a good point to remind you that, hey, you can go to the comment section and ask me questions if you need to, or you can find me on Twitter, chat with me that way. I should probably set up some other form of chat. Maybe I'll set up a channel of some sort so we can do that. So I'll figure that out and pop a link in the description below. All right, let's do our next example. Example number 2. In this one, I want to transform some sinusoids to phasors. If you didn't see the previous video, you probably were lost on the first example, but on the second example, you're definitely going to be lost, so go back and check that out to get the rules for the phasor sinusoid transform. So here's my two sinusoids. I is equal to 6 cosine of 50t minus 40 degrees amps, and part B is V is equal to negative 4 sine of 30t plus 50 degrees volts. So let's do this. Solution I. So to get I phasor, it's just going to be equal to the magnitude of this cosine, which is 6. Poor 6, so you're going to have to bear with me for a minute. 6, and then the angle, so the magnitude and the angle, as long as I'm in cosine form. So this is 6 angle negative 40 degrees amps. That one's not so bad. Part B is slightly more complicated because what I want is something that's in cosine form, and secondly, I also want to make sure that the amplitude here, I want to make sure this amplitude is a positive number. And the reason I want it to be a positive number is that it's going to transform into a magnitude. So I need to account for that in the angle of my system. So first thing we'll do is we'll get rid of that minus sign. So V of t is equal to 4 sine of 30t plus 50 degrees. And if I want to get rid of a minus sign, I just need to change the phase by 180 degrees, either by adding or subtracting. I'm going to add 180 degrees for now, and we'll see where we land on that. Now, V of t can be then written as 4 sine of 30t plus 230 degrees. Okay, so the next issue is that I'm currently sitting in sine form, but I need to convert it to cosine form. And I know that if I want to make a cosine look like a sine, I need to subtract 90 degrees. So V of t, which is in cosine form, would be 4 cosine of 30t plus 230 degrees minus 90 degrees. and that is equal to 4 cosine of 30t plus 140 degrees volts. Finally, I can convert this to phasor form. V phasor is just equal to 4 angle 140 degrees, taking the amplitude and the angle and then putting units on to make this 4 angle 140 volts. Whew. Example 2 is done. All right, now we can go in the opposite way, where we can find sinusoids if we're given phasors. So that's example number 3. Example 3 is find the sinusoids from the phasors. All right, so part A, I've got negative 25 angle 40 degrees volts is equal to V phasor. I've already broken a rule because I have a negative sign there, but we'll account for that when we convert. And then the other one will say I phasor is equal to J times 12 minus J5 amps. All right, so let's go ahead and solve this. In part A, it's more or less a straightforward application of the conversion between the two things. We'll first of all just notice that I've got a negative 25, so to make this a positive 25, I can subtract or add 180 to the angle. I don't care which way you do it. I'm going to subtract it because that gives me 25 angle negative 140 degrees. Now, to write this in cosine form, I'll take the amplitude, so 25 cosine. In this case, I don't know what omega is, so I'll just represent it using a variable. Omega t minus the angle 140 degrees. Volts is the units that I was given there. In part B, I'm going to do a very similar thing, except that I need to convert this rectangular form into polar first. So I'll first distribute out the j's, so I'll have J12 minus J times J5, which is equal to 5 plus J12. These J squared becomes minus 1, so I've got minus times minus 1. That's why I have a 5 there. All right, to convert this into normal polar phasor form, I'll take the square root of 5 squared plus 12 squared, and then, that's not a square, that's a degree, 12 squared, and angle inverse tangent of 12 over 5, and that gives me 13 angle 67.38 degrees. So I can just write the sinusoid form. It's equal to the magnitude 13 cosine of, again, no omega is given, so we'll just use the symbol omega, times t plus 67.38 degrees amps. All right, I've got one more example. We'll try to get that done now. So if I'm scrolling too fast, you can always go back and pause the video, double check that you have all the information written down. So in example 4, I'm going to give you two sinusoids given I1 of t equals 2 cosine of omega t plus 40 degrees amps, and I2 of t, which is equal to 3 sine of omega t minus 15 degrees amps. Let's make sure that's clearly a degree and not a 0, 15 degrees. I want you to find their sum using phasors. So first thing I need to do is I need to convert these into phasor form. I1 phasor is easy, it's 2 angle 40 degrees. I2 phasor is a little harder because I'm starting with the sine, but I know that I can convert this to a cosine by subtracting 90 degrees. So minus 15 minus 90. So this is equal to 3 angle negative 105 degrees. Now, to get their sum, I'm going to take I1 plus I2. These are both in polar form, so I need to convert them to rectangular form. So that's equal to 2 times the cosine of 40 degrees plus j sine 40 degrees. I'm putting these in parentheses to write this a little easier. Plus 3 times the cosine of negative 105 plus j times the sine of negative 105. So when I do this, I get roughly, and if I have one or two numbers that are a little off, I apologize, but I get roughly 1.53 plus j 1.286 plus negative 0.776 minus j 2.898. If one of these is a little bit off, if I have a rounding error or made some small mistake, I apologize. But when I add these together, I get 0.755 minus j 1.1 or 1.612, which is equal to, now, so you may say, hey, I've summed these up using phasors, I'm done. Well, the problem is that this gave me an initial set of results of sinusoids in the time domain, and what it really wants me to do is to go to the phasor domain, make the sum, and then take it back to the time domain. So that's what we're going to do. I need to convert this to polar. So this is the square root of 0.755 plus that squared plus 1.612 squared, angle inverse tangent of negative 1.612 over 0.755, which is equal to 1.77 angle negative 64.93 degrees amps. Again, I'm not done. I need to convert this back into the time domain. So this in sinusoid form is 1.77 cosine of omega t. The original omega was given just as a variable, so omega t minus 64.93 degrees amps. And that's it. All right, so that's all for this lecture. In the next lecture, we're going to talk about how we can look at phasors in actual circuit parts. We're going to talk about impedance and phasors in our different resistors, inductors, and capacitors, and then look towards applying that directly to AC circuits. All right, again, if you have any questions, drop something in the comments, or I'm thinking about starting a Discord chat. I might put that in my in the description below as well. If you want to join that, you'd be welcome to, and you can come and discuss and ask questions. All right, that's all for now. Thanks for watching.